This LearnElectrics video looks at finding earth faults in a domestic electrical circuit, although the principles can be applied to many electrical wiring faults. We show you two different methods and also offer other tips. Specifically, we are looking at earth faults in the video, answering questions like how do we trace an earth fault in a ring circuit, or do we have a problem between line and earth. The video follows on from part 1 of this mini-series on finding shorts. In the first part, we looked at shorts between live conductors in a ring circuit. This video will be on faults between line and earth conductors, or CPC, and there is an important difference between a short and an earth fault. It's all in the name that we call it. A short circuit is an unwanted low impedance path or connection between two live conductors, such as line and neutral, or between phase and neutral. In three-phase installations, we can also have a short circuit between two or more line or phase conductors. An earth fault, or ground fault as some call it, is a low impedance fault or path between a line or phase conductor and the earth or ground conductor. So this will be line to earth or phase to earth. If the fault involves the earth path, we call it an earth fault. A short and an earth fault are similar. It's all in the name. As an example, in this video, we will look at finding where a nail has pierced the sheathing and insulation of a twin and earth cable. As shown in the drawing, the nail is touching both the line and earth conductors. This is an earth fault. Just to remind ourselves from the part 1 video, before we begin any testing, we should always check that our test meters and leads are working correctly. First, with the crocodile clips joined together, the meter should read 0 ohms. Some meters can be nulled to read 0. Alternatively, make a note of any offset and deduct it from the measurements that are made. This proves that the meter is working and that the leads are in the correct terminals. Separate the crocodile clips and an open circuit will show as OL, out of limits, or some other meter maximum, such as 999 ohms as shown here. This shows what your meter will display for an open circuit, no connection. When testing a cable, any wiring that is separated from the circuit, a good result, will return a reading of OL or open circuit when we test between any two separate conductors, and we've tested between line and earth in this case. This is showing that there is no electrical connection between line and earth, which is what we want. When testing a twin and earth cable, it takes only seconds to check all three conductor combinations: line to earth, neutral to earth, and line to neutral, all of which should read OL or 999 ohms, or however your meter shows an open circuit. Shown here, we have an earth fault, where the damaged insulation is exposing copper conductor on both the line and CPC, or earth. There is contact, a low resistance path, negligible resistance between copper conductors, and this is just one example of an earth fault. Earth's metal backboxes can cause earth faults, especially if there are no rubber grommets in the entry holes and the insulation tears on the box. And the cables, they could be tight too, causing the line conductor to detach itself and make contact with the backbox. And this happens. We can have earth faults in lighting installations. Shown here is a correctly wired 3-plate ceiling rose. The CPC conductors have been insulated with green and yellow sleeving, so there is no exposed copper. And now this drawing shows a self-inflicted earth fault in the same ceiling rose. This time the installer has neglected to sheathe the bare copper earths either adequately or not at all. The bare CPC conductor must have green and yellow sleeving that covers all of the exposed copper CPC conductor. When the sealing row's lid is screwed shut, the conductors will be squashed together and may make contact with live terminals if these are not the insulated type. What are the first steps to finding an earth fault? In fact, do we even have a problem? An earth fault can cause the breaker to trip, but more often the 30 mA RCD is the one that will trip first, and we'll make that assumption here. Ask the customer if they've had any work done recently. This sometimes gives a clue to where to look first. If the RCD has tripped and cannot be reset, turn all the breakers off that are controlled by that RCD. Then turn the RCD back on. Then turn each circuit breaker back on one at a time, waiting a few seconds between breakers. When the RCD trips, you have probably found the faulty circuit. We're considering a socket ring circuit here, so begin by unplugging all the appliances from the circuit that is at fault. Reset the breaker and RCD. If the RCD still trips, then the circuit has a fault. Make sure that you know every socket on that circuit. Some electricians will mark the socket with tape and a number or letter. Safe isolation is the next step before we start taking any wires out or dismantling sockets. Assuming that we are certain the problem is in the wiring, we must carry out safe isolation and lock off the circuit under test or turn off the whole board if required. After proving safe isolation, then, at the consumer unit, remove the line, neutral and CPC conductors for the circuit. Inside the consumer unit, one end of the twin and earth cable we call the number 1 end, and the line, neutral and CPC are labelled L1, N1, E1. The other end of the same cable we call the number 2 end, and we have L2, N2, E2. It's important that we make this distinction when testing. Mix them up and we are in all sorts of trouble. With the 6 conductors removed from their connections, we have effectively isolated the circuit for the duration of the tests, and we can now be confident that any wiring tests will be done in isolation from the rest of the installation. We know the wiring is dead. We should begin by proving continuity. Without knowing that the conductors are continuous, any other tests that we make may be invalid. And we will make an assumption for this video that we are looking for a fault on a socket ring circuit wired in 2.5 square millimeter by 1.5 square millimeter copper twin and earth cable. With your meter set to low ohms, make a continuity measurement from L1 to L2. Depending on the length of the circuit, a small ohms measurement will be shown. In this case, shown here, L1 to L2 is 0.3 ohms, and we can consider the conductor as continuous from one end to the other. Now, low ohms end-to-end test the neutral. This measurement should be almost the same as L1 to L2. The copper conductors are the same cross-sectional area, or CSA, and go to almost the same points in the circuit. So N1 to N2 should read 0.3 ohms, and shown here this is acceptable. Now test E1 to E2, the earth or CPC. This time we have a reading of 0.5 ohms, and the question is, how do we know if this is a good reading? This CPC resistance measurement should be about 1.66 times bigger than the L1 to L2 test. The CPC is a smaller size conductor and therefore it will have a higher resistance. Doing the maths, if we put this into a calculator, 0.3 multiplied by 1.66 is very close to 0.5 ohms. We will look at other cable ratios of line to earth resistances later in the video, and trust me, it's easy. Having established that each conductor is individually continuous, we can now move on to the cross-checking between the different conductors. Low ohms test all three permutations of conductors. In a healthy, fault-free circuit, as shown here, there should be no connections. Everything should read open circuit, high ohms or OL. We are checking that line, neutral or earth are not cross-connected, and we should therefore have readings of L1 to E1 is OL, L1 to N1 is OL, and N1 to E1 is also OL. Because we've already proved continuity, there is no need to cross-check between the number 2 conductors. Now for a circuit with an earth fault. Carry out the same 3 low ohms cross-checks as before. This time, the meter shows a low resistance between L1 and E1, indicating an earth fault. The other 2 cross-checks show as a high resistance, OL, and are satisfactory. The fault is shown here as between L1 and E1, but if we had tested at the number 2 end, we would see that the earth fault now shows between L2 and E2. This is to be expected. In fact, any combination of line and earth will show the fault. But each measurement may give slightly different results. If we are going to trace the fault logically, we need to work logically. So L1 and E1 is what we shall use here. The conductor ends are in free air, and we can imagine the circuit now as just one straight line, much as a radial circuit, with the number 1s at one end and the number 2s at the other. I find that this approach makes it much easier to follow what is going on. And now we can move on to finding the earth fault. Just to reiterate that, the 2 ends of the same twin and earth cable are at the consumer unit, but separated from each other, and safe isolation has been carried out. The cable simply leaves the consumer unit, visits all the sockets and returns to the consumer unit. We can test just at either the number 1 cable, L1, N1 and E1, or we can test just the number 2 cable, L2, N2, E2, but we should not mix and match. Begin by low ohms testing between L1 and E1. Make sure that your meter has been nulled for non-zero readings, as we will now be looking at very small readings, typically 1 ohm or less. In this example, a reading of 0.156 ohms is shown between L1 and E1. This indicates that there is a fault between L1 and E1, but we don't know where. We will look at a couple of different methods to locate the fault. Method 1 will have us calculating the distance to the fault if we know what the fault resistance is. We can use the cable resistance tables to easily calculate a distance from the test point to the fault. In Guidance Note 3, this is table B1, and in the on-site guide it is table I1. The table gives you choices for different conductor size combinations. For this example, we have a 2.5 square millimeter line conductor and a 1.5 square millimeter protective conductor, the earth or CPC. Choose the row as shown by the red box. This tells us that these 2 conductor sizes have a combined resistance of 19.51 milli-ohms per meter length. This is a one-way measurement, not there and back. The numbers in the table take account of this for you. Using the resistance tables, we can calculate the resistance in ohms if we know the length. But we already know the earth fault resistance, and we want to know the length of the cable to the fault. So we can rearrange the equation, and now we can calculate the length. These are 2 very useful equations that are well worth making a note of. We need to use the equation for length to solve this one. Pause the video and take a moment to look at what the information boxes are telling us about the different numbers. Put the numbers in the right places and the calculation is easy. In the blue box, we now have 156 milliohms divided by 19.51 milliohms, and our calculator tells us the answer when rounded up is 8 meters. The fault is about 8 meters of cable from the test point. Method 2 uses a shorting link to locate the fault and must be carried out on a known dead and isolated circuit. Some electricians will test every socket for dead and mark it with tape before testing. No tape, no test. I prefer to use a plug-top test adapter. They are not expensive and readily available at most wholesalers. The big advantage is that for most tests you do not need to dismantle the socket or try to poke test probes past the socket shutters. A great investment that will pay for itself many times over in saved time. So, on your known dead circuit, use a plug-top adapter and link between earth and line, remembering to put the socket switch into the on position. Keeping that same image of a straight line circuit, test each socket for dead. It takes only seconds, and then label and mark each socket before starting, and do record your readings as you progress. Do not trust it to memory. We will make a low ohms measurement at the consumer unit as we move the shorting link between each socket until the readings do not change. Make the link between line and earth at socket A and measure the resistance between L1 and E1 at the consumer unit. 0.058 ohms is shown here, and this is less than the fault reading that we had. Move the shorting link from socket A to socket B and again measure the resistance L1 and E1. Socket B shows a reading of 0.117 ohms. This is still less than the fault reading. Now move the link to socket C and again measure the resistance between L1 and E1 at the consumer unit. The reading is now 0.156 ohms, the same as the fault reading. It could be that we've now passed the fault, but let's do one more check. Reposition the link between line and earth onto socket D and test again between L1 and E1. The reading has not changed. It remains at 0.156 ohms. Now we know for sure that we've passed the fault. The fault then is between socket D and the last socket tested that gave a different reading, socket B. We no longer need the link in socket D. This can be taken out. Now we must remove cables from the sockets for the next part. Start by removing the cables from socket C and test again. A reading of 0.156 ohms tells us that the fault is still there. The earth fault is in the wiring between sockets B and C. Double check that we've isolated the fault by testing at the other end of the twin and earth cable, that is to say between L2 and E2 this time. These number 2 conductors are already there at the consumer unit, so this is a very quick 10-second test. A reading of OL shows that the fault is not on the cables between socket D back to the consumer unit. The fault is definitely between sockets B and C. Now it's just a case of homing in on the fault, removing the damaged cable between B and C and replacing with fresh, undamaged cable. Before we go, we will look at finding the resistance ratio between line and earth conductors, or, as we should say, the ratio between line and CPC. If the line conductor and the CPC are effectively the same length, then use this method, and they should be the same length if the cable is twin and earth. The important thing to remember is that the conductor with a smaller size or cross-sectional area will have the greater resistance. The bigger size conductor has the smaller resistance, and if both conductors are the same size, then the resistance should be the same for both conductors. For example, say we have some lighting cable. Line is 1.5 square millimeters and earth is 1.0 square millimeters. We can find the ratio, in other words, how much more resistance the earth will have, by dividing the line size by the earth size. This will give a number greater than 1. The resistance increases. 1.5 divided by 1.0 is 1.5. So if the line measures 2.2 ohms, the CPC or earth should measure 2.2 multiplied by 1.5, which is 3.3 ohms. If our twin and earth cable has a line of 2.5 square millimeters and an earth of 1.5 square millimeters, 2.5 divided by 1.5 is 1.66666 and so on, which we can round down to 1.66 or round up to 1.67. It matters not which one you choose, the difference is hardly noticeable. So, if the line measures 0.9 ohms, what should the earth measure? 0.9 ohms multiplied by the ratio of 1.66 is 1.5 ohms. We say the earth or CPC will be about 1.5 ohms of resistance. And this one, if we are testing a cooker circuit and the line is 6 square millimeters and the earth or CPC is 2.5 square millimeters, what will the earth measure if the line reading is 0.5 ohms? The ratio is found by dividing the line size by the earth size. So 6 divided by 2.5 is a ratio of 2.4. Multiply the line resistance, 0.5 ohms, by 2.4 and we have an answer of 1.2. The earth resistance for this cable should measure 1.2 ohms. Line and neutral are both called live conductors. They both carry current in normal use. Live can mean either line, phase or neutral. The earth conductor in a twin and earth cable should be called a CPC, circuit protective conductor. A low resistance fault between the line conductor and the earth or CPC is called an earth fault, not a short, although you will often hear it incorrectly referred to as a short to earth. Be methodical in your testing and always work safely. There are several methods used for effective fault finding, and you will come across others and may even develop your own preferred methods. And practice is the best way to make fault finding easier and part of your skill set. Thank you for watching, it really is appreciated, and I hope that you found this video useful and informative. Please subscribe to our channel to get access to all of our videos, and remember to click on notify to be sure of not missing our next video. And you will find even more information, videos and help on our website at LearnElectrics.com. And don't forget, you can also type in LearnElectrics, all one word, into the YouTube search bar to go directly to our channel at any time from any computer. We are constantly adding new videos to our channel, so don't miss the next one. And once again, thank you for watching, and we hope to see you again very soon.